In this module, we will be discussing the applications of free electron model and Huckel molecular orbital theory to electronic spectra of some representative molecules. Firstly, you will learn about the theories of pi-pi star transitions, and you will learn about the free electron model and its applications to linear polyenes. The HMO theory, which is the Huckel molecular orbital theory, and its applications to ethylene. And finally, you learn about the use of symmetry to predict whether a transition is allowed or forbidden, and if it is allowed, what is its polarization. Several theories were proposed in the previous century to theoretically explain the observed phenomena with regard to pi-pi star transitions. Two simple ones: the free electron model, also called FEM, and Huckel molecular orbital, also called HMO method, which lend themselves to easy computation, are described in this module. Coming to the theories of pi-pi star transitions, almost all theories are based on the concept of sigma pi separability, as they occupy different domains. The sigma and pi electrons, they occupy different domains. The sigma electrons are in the molecular plane and the pi electrons have nodes there. That is why they cannot interact. Because of this, they cannot interact with each other and thus may be treated independently of each other. Also, since the pi orbitals are higher in energy than the sigma orbitals, which you already know, they are more tightly held to the nucleus, the sigma orbitals, and that is why the pi electrons are held responsible for the reactivity of a molecule. Hence, we consider only the pi framework while considering unsaturated systems. We do not consider the sigma electrons because they are more tightly held to the nucleus. They do not participate in the reactivity of the molecule, and so we ignore them when we are studying pi electron systems. We first begin with the free electron model of linear polyenes. The free electron model is based on the particle in a one-dimensional box model, which we have studied in quantum chemistry. Briefly, in this problem, an electron is assumed to be trapped in a one-dimensional box of length L. The electron can move only in one dimension, but it is trapped in a box and the length of the box is L. And you have done the quantum mechanical solution, and you know that you get wave functions psi n, where n is a quantum number, and the normalized wave functions are square root of 2 by L sin n pi x by L, and the corresponding energies E n are given by n square h square by 8 m L square. I have written me here to denote that this is an electron, so the mass is that of an electron, and n is a quantum number which you know can assume only integer values, and these are 1, 2, 3 up to infinity. The first two wave functions we have shown in figure, and you can see that the first wave function n is equal to 1 is positive throughout, and for n is equal to 2 there is a node at L by 2. Now we will consider the molecule ethylene. Ethylene, as you know, has a C double bond C, and then there are 4 hydrogens, and the Cartesian coordinates that we take are based on how we take them in group theory. This molecule has D2H symmetry. There are 3 C2 axes, but the one which passes through the 2 carbon atoms will be labeled as Z, and then we define Y as the one which will define the molecular axis, which becomes the YZ axis, and X is perpendicular to that. So, each carbon atom is sp2 hybridized, and which are the orbitals which are involved in this hybridization? One is the 2s electron, and then the electrons which are in plane, which are the p orbitals py and pz. So, 2s, 2py and 2pz orbitals are involved in sp2 hybridization, and 3 bonds are formed by each carbon atom in the molecular plane, one with each of the hydrogen atoms and one with the carbon atoms. This is the sigma framework of the molecule. Now, what happens to the 2px electrons? These are 2px orbitals are perpendicular to the plane of the molecule, and they contain 1 electron each, because the remaining electron of carbon atom out of the 4 valence electrons is held in the 2px orbital. The 2 orbitals of the 2 carbon atoms, they can overlap, and in two ways they can form a bonding orbital, pi bonding orbital, or a pi star antibonding orbital. Now we extend the pi system by adding two more carbons in conjugation, that is we form butadiene. The next polyene is butadiene, which contains 4 carbon atoms. You take 2 ethylene molecules and you combine them, you should get butadiene molecule. Now this is a polyene having alternate double and single bonds, and you can continue this process by adding more and more, 2 carbon more you will get hexatriene, and 2 carbons after that will give you octatetraene, and this can be done indefinitely. Now you will see that in butadiene there are 2 different isomers which are possible. One is the trans isomer and the other is the cis isomer, which is shown on the right. Each carbon in conjugation, you will see, contributes an electron to the pi electron system, just like ethylene, where you had 1 electron in the 2px orbital of each carbon atom. Each carbon atom which is involved in conjugation will contribute 1 electron to the pi electron system. Now in the MO method, these electrons do not belong to the atoms from which they have come, but they belong to the whole molecule, because the molecular orbital is spread over the whole molecule. Thus we may think of them as being delocalized over the entire molecule. Now conservation of orbitals requires that an n atom polyene, where there are n atoms in conjugation, will give rise to the same number of molecular orbitals, that is n, and out of that n by 2 will be occupied by 2 electrons each, and because each orbital can take 2 electrons, so half of these are occupied. When a transition takes place, it takes place from the occupied orbitals to the unoccupied ones, and of course the transition depends upon selection rules. Now when you are applying the free electron model, what is the length of the polyene that you must take to define the length of the box that you are talking about? This is some matter of controversy. If you want it to be the distance between the 2 end carbon atoms, that will be wrong, because this means that the wave function becomes 0 at the, because these are the boundaries at these carbon atoms, the wave function will go to 0. Now that means you should add a little distance to each side of the 2 carbon atoms. If you add 1 bond length to each side, it gives the best correspondence with the wave functions obtained by another MO method that we will be talking about, the Huckel molecular orbital method. Each bond length is taken as the average of a CC single and CC double bond, because you have alternately 1 single bond and 1 double bond, and so we take the average carbon-carbon single and double bond length, and that is the one in benzene, which is 140 picometer. Now let us take the example of hexatriene. There are 6 carbon atoms in conjugation, and if there are n atoms, there will be n minus 1 bonds, and so there are 5 bonds. We add 1 bond on each side, making the number of bonds 5 plus 2 7. Therefore the length of the box will be 7 into 140 is equal to 980 picometers. 6 electrons occupy the first 3 energy levels, so that the longest wavelength transition is n is equal to 3 to n is equal to 4. There were 6 carbon atoms in conjugation, and that means there were 6 molecular orbitals that we obtain, and there are 6 electrons to be put in these molecular orbitals. 2 electrons in each molecular orbital means that the highest occupied level is 3, and the longest wavelength or the shortest energy transition is from the 3rd energy level to the 4th energy level. In general, for a polyene having n atoms in conjugation, the highest occupied molecular orbital, which is also given a name HOMO, is k is equal to n by 2. Its number is equal to k is equal to n by 2. The longest wavelength transition will be from this level to the next one, that is from k to k plus 1. The difference in energy between the k plus first level and the kth energy level, that means delta E is equal to Ek plus 1 minus Ek, and which is equal to k plus 1 square h square by 8 me L square, which is the energy of this orbital, minus that of the lower energy level k square h square by 8 me L square, which is equal to 2k plus 1 h square by 8 me L square. And what about the wavelength? We know that the wavelength delta E is equal to h nu and nu is equal to c by lambda. So lambda is equal to hc by delta E, and this turns out to be 8 me L square C by H into 2k plus 1. Now you will notice that all of these are almost everything is a constant except k and the length of the box. You substitute all these values for the hexatriene problem, and what you find is that lambda turns out to be 452 nanometers, but when you compare with the experimental value, that is only 258 nanometers. Obviously, there are some assumptions that we have made in this model which are incorrect. The first one is that the polyene chain is not linear, but it is zigzag as we had shown for butadiene, and this reduces the length of the chain because instead of being a stretched out chain, it is a zigzag chain, and that is why we should not add one bond length on each side. You add half a bond length on each side instead of one. That means the box length is decreased and the value of lambda is increased to 333 nanometer, which is in better agreement with the experimental value. Though the agreement with experiment is not too satisfactory, the FEM manages to explain the effect of conjugation, since increasing conjugation increases L and the wavelength is proportional to L, and since both L and 2k plus 1 depend on the length of the carbon chain. So you have L square in the numerator and 2k plus 1 in the denominator. So that means it is roughly proportional to L. As you increase the conjugation, the longest wavelength transition lambda also increases, and this is what we expect to be the effect of larger conjugation. Once we have got the energy separation, the next thing is to find out what are the selection rules. Now we had assumed that the longest wavelength transition from the HOMO to the lowest unoccupied molecular orbital, which is also called LUMO, is an allowed transition. Just now when we had found out the energy of the 3 to 4 transition, we had assumed that this is an allowed transition, but is it allowed? We will use symmetry arguments to show that this is actually the case. It is an allowed transition, and to get the selection rules, it is more convenient to shift the origin to the center of the box, and to balance the charges we place a proton there, so that you have a proton at x is equal to 0 and the box extends from minus L by 2 to plus L by 2 and its length is still L, and the wave functions also look similarly, but it is more convenient to use this to find out the selection rules. Since the position of the electron is given by x, the dipole moment is the charge multiplied by the distance between the two charges. That means it is equal to Ex because the proton was at the origin and A is the electronic charge. The transition dipole moment, you know, is given by, for a transition from the Lth state to the Mth state, is given by E, which is the electronic charge. The integral from 0 to L, because this is the domain where the electron can stay, psi m x into psi L dx, and in this triple product within the integral, the middle term x is always odd. You know that x becomes minus x when you reflect it through the center. So it is an odd function always, and the wave function corresponding to n is equal to 1 you have seen is an even function, because when you reflect it through the center it does not change sign. But the next one, psi 2, is an odd function, because in this case you find that one half of the wave function is positive and the other half is negative, and this is something that you will find for all the wave functions. Psi n are odd functions for even n and they are even functions for odd n, and this is true for all values of n. So it means that the triple product will be even only when the product of the two wave functions is odd, which is possible only if one of them is odd and the other is even. Therefore, the transition from the HOMO to the LUMO is always allowed, because if one of them is even, the other will be odd because it is the next energy level, and vice versa. Also, odd to odd n and even to even n transitions are forbidden. So this is the selection rule that we have found, that the transitions will be allowed from even levels to odd levels and from odd to even levels. We will find that this is not actually true. Not all of these transitions are allowed, but at least the HOMO to LUMO transition is allowed in the free electron model. Then we come to the next molecular orbital theory, and this is the Huckel molecular orbital theory, or the HMO theory. This is the other approach, and we first use the help of symmetry to obtain the selection rules for some molecules, and then use HMO theory to predict the transition energies. If you recall, HMO theory gives you the energies of molecular orbitals. To get the selection rules, we'll need to know the symmetries of the orbitals, and we'll use group theory to do that. As you know, the HMO theory applies only to pi electron systems. We begin with the simplest pi electron system, and which is ethylene, or also known as ethene, and look at the wave functions. You have chi1 and chi2 signifying carbon atom 1 and carbon 2, the 2px orbital on carbon atom 1 and the 2px orbital on carbon atom 2, and the molecular plane, as you know, as we had seen earlier also, is YZ, and the pi orbitals comprise combinations of the 2px orbitals on the 2 carbon atoms, and we have labeled them as chi1 and chi2. The molecular point group we have already seen is D2H, and these are the various symmetry elements. There is the identity operation, a C2 operation passing through Z, another one through Y, another one through X. Then there is a center of symmetry, and then sigma xy plane, sigma xz plane, and sigma yz plane. And we now examine the behavior of chi1 and chi2 under the various operations of the D2H point group. So look at chi1. When you perform the identity operation, obviously it remains chi1, but when you rotate it through a C2 rotation along the z axis, it changes sign because it reverses direction. So it becomes minus chi1. Similarly, along C2y, not only does it change sign, it also exchanges position with the chi2 orbital, the other carbon atom. So it becomes minus chi2, and C2x, because it is 2px orbital, will not change sign, but they will exchange positions, so it becomes chi2. Similarly, under I operation, chi1 becomes minus chi2, the lobes also reverse direction, so the sign is changed and chi1 is replaced by chi2. Sigma xy, similarly reflection in the xy plane, because it contains x, will not change the sign, but chi1 will become chi2. Similarly, xz also, it will not change sign, it will also remain where it is, so it will be chi1, and sigma yz will become minus chi1. And similarly, you can go through chi2 and you will find that under the various operations, chi2 sometimes remains same, sometimes changes sign or reverses sign, and also changes position with chi1. And to get the reducible representation, we only count the number of orbitals which are unchanged. For example, in E, chi1 is unchanged, chi2 is unchanged. So there are 2 unchanged orbitals. The reducible representation, the character is 2 for E. Chi1 remains chi1 but changes sign, and similarly chi2 also remains in position but changes sign. So the total character is equal to minus 2, but in the C2y, C2x and I operations and sigma xy operation, what happens is that they exchange positions, so they do not contribute to the diagonal, so the character is equal to 0, and similarly for sigma xz you can see it is 2, and sigma yz it is minus 2. So since both orbitals remain unshifted under E, the character is plus 2. Rotation about the z axis reverses the signs of the 2px orbitals but leaves them unshifted, so the character will be minus 2. In a similar way, rotation about the y axis not only reverses the sign of the orbitals but also shifts them, and hence the character is 0. For this operation, in the same fashion, the remaining entries can be satisfyingly obtained. Now, when you resolve the reducible representation, you find that it is equal to B3U plus B2G, and then to find out the combinations corresponding to B3U and B2G, we use the projection operator method, and after normalization for B3U, you find that the wave function psi B3U is obtained by multiplying the character of B3U for the E operation and the result of the E operation on chi1, and similarly for C2 Z and so on. We do this and we find that the combination is 1 by root 2 chi1 plus chi2, and for the B2G the combination is 1 by root 2 chi1 minus chi2. These two wave functions are shown in figure. You can see the projection in the YZ plane is also shown. Psi B3U you see is a bonding orbital because the electron density is spread if you take the maroon color as the positive lobe, the green color is the negative lobe, and both the lobes are delocalized over the 2 carbon atoms. This is a bonding orbital, and the one on the right, B2G, you find that the plus and the maroon and the green regions, they are separate from each other, so it is an anti-bonding orbital. So the one on the right is an anti-bonding orbital. It is the B2G orbital, because you find that the overlap is negative between the 2 carbon atoms. So we call it the pi star orbital, and the first one as the pi orbital. So that means that the positive combination increases the electron density between the 2 carbons, and psi B3U is therefore a bonding or a pi orbital, but in psi B2G there is a nodal plane between the 2 carbons, and hence it is an anti-bonding orbital. Now we use HMO theory. You obtain the secular determinant for ethylene, and you know that wherever there is a carbon atom, we put an alpha value, and wherever there is a bond between 2 carbon atoms, that is 1, 2, there is a bond, so you put a beta. Similarly 2, 1, there is a bond, and then we diagonalize it, and we obtain 2 values of epsilon, the orbital energies, and these are equal to alpha plus C2 by C1 beta. For psi B3U, C1 is equal to C2 is equal to 1 by root 2, the normalized coefficients, and hence epsilon 1 is equal to alpha plus beta. Similarly for psi B2G, C2 is equal to minus C1, and C2 epsilon 2 is equal to alpha minus beta. Now both alpha and beta are the pi electron energy of an electron in the 2p atomic orbital of carbon and in the bond region, and therefore they are both negative in sign, because these are the bound regions. Hence B3U orbital is lower in energy, and obviously because it is a bonding orbital, this is what you expect, that B3U should be lower in energy. So E1 is equal to alpha plus beta is B3U, and B2G is alpha minus beta, and the energies of the 2 carbon atoms, independent isolated carbon atoms, is alpha. So overlap with the 2 carbon atoms has resulted in a bonding orbital alpha plus beta and an anti-bonding orbital with energy alpha minus beta, and remember that both alpha and beta are negative quantities. So alpha plus beta is lower than alpha minus beta. The transition energy for the transition of an electron from the bonding molecular orbital to the anti-bonding molecular orbital is therefore minus 2 beta, and do not worry, beta is negative, so it is still positive, and the energy is given by 2 beta, and this is the pi star transition in ethylene as we have shown in figure. Now what value for alpha and beta to use? Now you know that in HMO theory we use values that give you best fit with experimental values, and the values that are obtained for beta, there are various values that different people have used, but one that is very often used is minus 2.4 electron volts, and that means delta E is equal to 2 beta, it is equal to 4.8 electron volts, and when you convert it into wavelength, its lambda is equal to hc by delta E, and this will be 6.626 into 10 raised power of minus 34 joule second into 2.998 into 10 raised power of 8 meter per second, and multiplied by 4.8 electron volt, which was delta E, and into 1.602 into 10 raised power of minus 19. This is the conversion factor from electron volt to joules, and you get 1.240 into 10 raised power of minus 6 divided by delta E, and this turns out to be 2.583 into 10 raised power of minus 7 meters, or this is 258 nanometer, and the observed wavelength is 190 nanometer, which is much shorter than the calculated value. However, made a number of assumptions, and considering the number of approximations involved and the uncertain value of beta, there are values people have used minus 0.78 to minus 2.7 electron volt. So any one of these values could have given you a better fit to the experimental value, and at least you can say that there is some qualitative agreement. Now we come to the selection rules. The ground state electron configuration for ethylene is therefore B3G twice 2 electrons in this orbital. Since this is a closed shell, the ground state is 1A1G, When you promote an electron to the B2U orbital, it results in the electron configuration B3G1, B2U1. The electronic state is obtained, as you know, by direct product B3G into B2U. When you do this product, you get B1U, and you know that two spin states are possible, singlet and triplet, because they could be parallel spins or they could be anti-parallel, depending on whether the spins are anti-parallel or parallel. Therefore, the states are 1B1U and 3B1U. Transition to the 3B1U state is not allowed by the spin selection rule, which says that delta S should be equal to 0. So, we started from a singlet state, we can only end at a singlet state, and that means for the transition 1AG to 1B1U, the transition dipole moment is what we need to find out, and this is given by the product of the ground state AG into B1U is equal to B1U, because AG is totally symmetric. We look for a matching representation among the Cartesian components and find that Z also transforms as B1U. That means when you multiply B1U by B1U, you will again get AG. That means that the transition is allowed and it is polarized in the Z direction. You can also think of double excitation, where both electrons are excited simultaneously, and this leads to the electronic configuration of the excited state as B2U twice. The product of any representation by itself is always the totally symmetric representation, and that means that the resulting state is 1AG. The ground state also was 1AG. That means that the transition from 1AG to 1AG, it is forbidden by the Laporte selection rule, because it is a G to G transition which is forbidden. Thus, only one pi star transition is allowed for ethylene, and this is the one that you observe at 190 nanometer. So, we will summarize what we have learnt in this chapter. Of the several theories of pi star transitions, the free electron model and HMO theory are some of the simplest ones. The free electron model correctly predicts the effect of increasing conjugation on the transition wavelength, but is not quantitatively correct. The same is true for HMO theory. Symmetry helps us determine whether a transition is allowed or forbidden, and if allowed, what is its polarization.